So now we're going to look at exercise hello triangle indexed, which is 2.2. And if we run it, it's actually not rendering a triangle. Well, it's rendering two triangles that form a rectangle. And while we could render two triangles just like we rendered a single triangle before, this time instead of calling GL draw arrays, we're calling GL draw elements. And what draw elements does differently is that yes, it expects a VAO, which we have set up. It expects a shader program. But it also expects a buffer of indices. The indices are indexes into the vertex data, such that we construct our primitive, in this case a triangle, by specifying 3 indices. So if we look up at our vertices array, we're going to end up forming 2 triangles, yet we're only specifying 4 vertices. And then in our buffer of indices, we're going to have first a triangle made up of index 0, 1, and 3, meaning this vertex, and then the one at index 3. And then the second triangle is formed from 1, 2, and 3. So it's formed from these 3 vertices. Without these indices, if instead we were using GL draw arrays, then here we would have to have 6 vertices, 3 for the first triangle, 3 for the second. And that would mean that the vertices at indexes 1 and 3, they'd have to be repeated in the vertex data. That may not seem so bad with a small set of vertices, but if you imagine for a much larger model, you're going to typically have many, many more shared vertices that are going to have to be stored redundantly. And also the problem is that, as we'll see later, our vertices are going to be accompanied by attribute data. So each vertex might end up being something significantly more than just 3 floats. It might end up being 12 floats or beyond. So it's an even greater savings then if we don't have to store redundant vertices. So now, as I said, everything in this example is exactly the same, except now we're going to have something you might call an element buffer object, which will have the indices data, and this has to be set up before we call GL draw elements. So here, when we create our VBO and our VAO, nothing is changing there, except now we also have another buffer for EBO. We're binding the VAO just like before, setting up the VBO just like we did before, same attrib pointer setup. That's not changed at all. But now for EBO, we're going to call GL bind buffer, this time specifying type element array buffer, not regular array buffer, as we do for our VBOs. And having bound this buffer, we then want to put the indices data into it, just like we do with buffer data here for the vertices, except again here you're specifying element array buffer, not a regular array buffer. And so now the EBO is actually ready to go. We don't associate it with a VAO the way we do with the VBO. VAOs do not make reference to these element buffer objects. Instead, it's simply the case that when we call GL draw elements, whatever is currently buffer bound with GL element array buffer, that is understood by draw elements to be where the indices are specified. In fact, if we don't have EBO bound at this point, if there is no currently bound element array buffer, then this call would crash. Note that we're specifying, of course, the type of the primitives. This is the number of vertex indices that are going to be read. This is the type of the indices, not the type of the vertices themselves, the type of the indices. They're unsigned ints. And the 0 here is an offset, so you can have it read from some index other than the first index. So that's all that's different here, except one last thing. We created the EBO, so we should also delete it like any other buffer when we're done. So we call delete buffers down here with EBO. So now let's look at exercise 3.1, shaders uniform. And here it's rendering a triangle, but if we wait a moment, you'll see that it's actually changing its color, pulsing slowly over time. The first thing that's different here is in our fragment shader, we now have this variable of type vec4 called ourColor, and as it says, it's a uniform variable. Uniforms are variables in our shader program that are global throughout the program, and in fact are not allowed to change in the running of the program. And before we run the program, before we call draw arrays or draw elements, we have to set up the values for the uniforms first. They're basically inputs from outside the shader program. And be clear, when we say they're unchanging during the run of the program, that's the shader program, which runs once each frame. So frame to frame, in this example, we're changing what the ourColor value is. And as you can see in the code, it's simply taking whatever the ourColor is from the uniform and setting that to be the frag color. looking down at the loop, we've actually in this case gone back to draw arrays. We're not using draw elements and we're not using indexes anymore. We could, but there's no reason to do so, so we're just going back to the more straightforward method in this case. But before the draw call, we're calling GL uniform 4f. 4f here means a vector of 4 floats. Because OpenGL is codified for C and C doesn't have function overloading, it's the case that in OpenGL you have a number of functions where there are many variants for different kinds of input. So this is the version of GL uniform that takes in a vector of 4 floats, which are these 4 float values here. And when you call GL uniform, the shader program whose uniform we are setting has to be the currently enabled program. So we have GL use program up here for our shader program. But the call also has to specify which uniform variable we're setting the value for, because there could be many. So that's why here you're specifying vertex color location, which is just an int value that has been defined up here by call to get uniform location, pass in the shader program, and the name of the uniform variable, which in this case is our color. And be clear that uniform location actually is not changing frame to frame, so this could just be done outside the loop. So that's how we set up a uniform value. And in this specific case, the uniform is being used as a color value where the red is 0, the blue is 0, the alpha is 1, and the green value is going to vary frame to frame based on the current time, which we're getting from GLFW, and then using a sine function to have it vary in a pulsing gradual transition way. Sine, of course, always returns something in the range of -1 to +1, and so frame to frame, the green value is pulsing up and down from black to a certain green shade in a smooth curve. Now I did say that uniforms are not meant to be mutated in the course of the shader program, so let's actually see what happens if we do try and mutate the uniform here. I'm going to modify our color, just set it to this white value, save. I'm going to come over here and build the project, run the program. And well, it didn't crash the program, but you can see in the console we have some errors now. There's first a compilation failure, and then of course, because it failed to compile it, we also can't link. And it's telling us that there's an assignment to uniform our color. And you're just not allowed to assign to uniform, so that's why that's invalid. So the compiler caught the error. Now let's look at example 3.2, shaders interpolation. I'll run it. And you can see we get a pretty rainbow triangle. So what's going on here? Well, firstly looking at the shaders, whereas before we just had the one input to our vertex shader, now we have a second input. Notice it says location 1. This is going to be a color value, as the name indicates, also a vec3. Also now, in addition to assigning to GL position, which is just an automatic variable that is created implicitly, we don't have to create it ourselves, it's always there. We're now creating another output variable called our color vec3, which is going to be passed down the pipeline. So if we had geometry and tessellation shaders, we could get this value there, but we don't have such shaders. We do, though, of course, have our fragment shader, and so our fragment shader needs to accept as input now our color. And I believe the fact that the name and type matches is significant. I'd have to test this and look at the docs. I can't see any reason why you'd make them not match. It otherwise, I think, might have to do with the ordering. So if we had multiple output variables, multiple input variables, they may just match up in order. I think it might work that way instead, actually. I'd have to check. Anyway, as we have it configured here, it works. Output of our color is going to be accepted as input here. And now in the fragment shader, when we set frag color, we're setting it to the our color input. But understand in the output shader, for each vertex, we're spitting out a different color. And for a triangle, then the question is, well, what does the fragment receive? For a pixel within a triangle, which of those colors do we get? Well, what we get is the interpolation thereof, the perspective correct interpolation, as we discussed in earlier videos. In the whole rasterization process, the hardware is figuring out how to interpolate these values in a perspective correct way. And that's what we get here as input to our fragment shader. So aside from the shaders being different, what's different in our rendering loop? Well, the rendering loop is nothing new here. It's just like our actually earliest example. We're just rendering the triangle as currently configured by the VAO. No indices this time again, we're just using draw arrays. So nothing new here, but if we go look at our vertices array, now it contains not just positions, but colors. And notice the layout where it's for each vertex, it's first the position, the 3 floats, followed by 3 RGB floats for the color. And whereas before we just had one vertex attrib pointer call specifying where the vertices are and how they're laid out in the array, now we're going to have a second vertex attrib call. Notice it says index 1 specifying how the colors are laid out. And this top call actually also changes because where it was here 3 times size of float for the stride because the positions were just spaced 3 floats apart. Now they're 6 floats apart. It's from here to the next one, right? Well, same thing for the color attributes. They are spaced 6 floats apart. Here to here is 6 floats. But we also need to specify an offset that starts here because this is where our first color is, of course. So that's why this is a void pointer of 3 times size of float, not 0. And do not forget to call enable vertex attrib array, otherwise it would not go into effect. So having set up both the indexes of VAO, index 0 and index 1, for the vertex data itself, and then the attribute of the color, when the shader gets called, it's going to receive 2 inputs. One at location 0, as in index 0 of the VAO, and the other at location 1, index 1 of the VAO, which is our colors. So again, understand the relationship between the VAO and the VBO or VBOs is that the VAO is a structure of, I believe on most OpenGL implementations, the max is capped at 16. I believe that's usually the case. So you can have up to 16 indexes for your VAO, potentially pointing to different VBOs, but in this case it's just 1. And for each index in the VAO, it also has information about how the data is laid out within the buffer. That's why when we come down to the draw call, we don't need to have the vertex buffer object bound, we just need the vertex array object bound because it internally has references to any relevant VBOs. And I believe actually in the prior video I may have said it was safe to delete the VBO before this call. Well, I think we got away with it in that prior example because there aren't any subsequent allocations on the GPU side that might potentially overwrite the memory that VBO was occupying. But in a larger program, it might be the case that if you delete the buffer, I believe just like when you might manually free memory on the CPU side, the danger is that that chunk of memory might subsequently get overwritten by later allocations. So while the data of this VBO is in use, even though we don't need to have the VBO bound, I believe it's the case that it's not safe to delete it. So we should only delete the VBO here when we clean up. So let's run the program again and see this top vertex. This was set to the color of RGB 001 as in full blue. This here was 010 as in full green. This was 100 as in full red. And then for the fragments in between, for the pixels in between, it's interpolating between those color values. That's why it smoothly transitions and you get the full colors of the rainbow all in this one triangle.